Welcome, everybody, to the Boat Project. Boat Project is a long-term, usually about 6-week construction project, just because we have to wait for the glue to dry each day, which is why you're grouped with people who are also working together on the final project. The idea is you do some gluing, you get as far as you can on a given day, and then you can start working on your final project with your partner if you have one. The boat project itself, here's some pictures from a couple years ago. I think I've already shown you probably some video clips from last year. The key on this one is simply being able to have one of your members in your group sit in it, doesn't matter who it is, and then make it across the short length of the pool without sinking. You are simply hand propelling it. You're not allowed to touch the sides. You would need to have some balance. And hopefully it holds together as long as you make it. So the construction project, you can sort of read about it real quick. Single or double person boat with a quantity of limited material. Honestly, all of you probably want a single person boat. You're going to be given 10 strips of very thin plywood that are 8 feet long and half an inch by a quarter inch to make the frame. And you're given 40 square feet of thick paper that you're going to coat the outside frame once you get it completely done. And then finally some paint to make it waterproof. In this case, it's going to be acrylic paint. That's actually what's going to make the thing waterproof. You are going to be given wood glue. You could use liquid nails. No one used it last year. You can't use any fiberglass adhesives or resins or joint clamps inside of the boat itself. Yes, you can clamp it while you're gluing it, but not during the other parts. 2 or 3 people per boat project. Just wood glue at the joints, not coating the wood strips. Why? You're going to add too much weight to your boat without giving it any strength. No nail, staples, screws, string, or other kind of fasteners. Why? We can't let any of that material get into the pool if it does go. No resins that can be used, as mentioned before, only varnish or lacquer. And the design of the boat must be boat-like, with sides that lead to a flat bottom or an edge. Surfboards, rafts, pontoons, or any designs where the navigator might lie down or lay down is not qualified. A canoe-style boat with angled bottom is acceptable. All materials must be completely dry in order to enter the pool. Your paint can't be wet anymore. The water line must be clearly visible and may not be more than 1 inch thick. Your boat must have a theme. Any skits that accompany the boat crossing must be no longer than 1.5 minutes. Your boat must be hand-propelled, no oars, sails, motors, etc. Skits, music, slogans must be approved. So we already talked about it. I'll supply the strips of wood, the paper, and some paint. If you want to bring your own paint, you can. But yeah, it's kind of fun. Couple conversions you need to know in advance. Please realize that 1 square meter is 100 centimeters by 100 centimeters, or 10,000 square centimeters. Whereas volume, 1 cubic meter, is 100 by 100 by 100 square, and ends up being 1,000,000 squares or cubic centimeters. Please make sure you keep track of the difference between these. A lot of people get confused with the conversions. Finally, 1 cubic centimeter, you might remember from chemistry, is 1 milliliter. 100 cubic centimeters is 1 liter. And 1,000,000 cubic centimeters would be 1,000 liters, or 1 cubic meter, as we mentioned above. Again, just a quick reminder from chemistry, 1 milliliter of water has a mass of 1 gram. And so because of that, you can do some quick conversions here. 1,000 cubic centimeters, or 1 liter, 1,000 milliliters, have a mass of 1 kilogram if it's pure water. Pressure is force over area, and you may have learned this back in chemistry. Why do I have a picture of stiletto heels? Well, believe it or not, the pressure exerted on the floor by the stiletto heel is the same as the pressure of an elephant stepping on a floor, which is why stiletto heels will leave dents in linoleum floors like the ones in this classroom. It is that much pressure. The units for pressure are pascals. Officially, remember, force in physics is measured in newtons. Area is measured in square meters. And so the units are newtons per square meter, which is, because it's so commonly used, is called the Pascal. Abbreviated capital P, small a. It's a very small unit. So typically in chemistry and physics, we usually talk about kilopascals or even megapascals. Real quick in passing, the units in the US are pounds per square inch, pounds being unit of force, square inches being the unit of area, abbreviated PSI, pounds per square inch. One quick thing before we leave this one, these two identical blocks, one is sitting on its edge over here, and the other one is sitting on its side. Quick question before you go on, just a conceptual check. Which one of these is going to exert a greater pressure on the table? Well, since they're the same block, the force of gravity is going to be the same on both of these, but please realize that this one has a greater area of contact with the table. Therefore, the pressure on the one sitting on its side is going to be smaller than the pressure of the one sitting on one long edge, like here. Same force, smaller area. You can actually define liquid pressure as this equation. We'll come back and look at this again later. Liquid pressure is equal to the density of the liquid you're dealing with times gravity, 9.8 meters per second squared, times the depth in meters that you're working with. So it depends only on the depth, assuming that density and gravity don't change. So which of these dams have a greater pressure acting on them? The answer is the deep one. Even though it's small but deep, the pressure down here is going to be much larger. In fact, twice as large as the pressure just 3 meters deep. So this one has more pressure. It turns out also, depending on the length of this dam, probably more force on it. But it depends not on the volume, but just on the depth. Quick question on this one. Where is the pressure greater? Here, 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 or here? And you might already guess already. It turns out the depth is exactly the same for all four of these. The depth is measured straight from the surface down that point. It doesn't matter what the shape of the container is directly above it. All of these 4 points have the same exact depth. Therefore, the pressure is going to be the same. And yes, the height of the liquid is the same. If pressure was greater in one of these, water would rush from that to the other ones, and the depth or the height of this would not be the same. Interestingly enough, the pressure is actually different the deeper you go. So, for example, the pressure down here is greater than the pressure that you would have here on this top part. Why? This part right here is at a lower depth, less depth below the water than the one at the bottom. And even this one would be even smaller, and it's not drawn very well because of the even smaller depth. What does that do? It means that we've got forces acting on all these surfaces. The one at the lower edge here is going to have a greater force on it. What does that tend to produce? For most submerged objects, actually for all submerged objects, there is always going to be a net force towards the surface. Why? Because the bottom is experiencing a greater force against it than the top surfaces are. What's that force called? It's called the buoyant force, and we'll talk about that in just a second. If you put holes in the side of a water glass or a water jug, you would discover that the water in the top doesn't flow out with a very large velocity, whereas the one midway down would have a larger velocity, and the one at the bottom would have a very large velocity. Why is that? Because the pressure is smaller here, smaller depth, greater here, medium depth, and even greater here because of the much greater depth. And you can actually see it because of the velocity of the water coming out the edges. Here it again is an example. This rock, or almost looks like a potato, has forces acting on all of it, or pressure acting on all of it, but there's a greater pressure acting on the bottom, producing a net upward force on this thing. That upward force is called the buoyant force, and it's a consequence of the pressure increasing with depth on an object. And so who first figured out how much there's a relationship between the buoyant force and the amount of liquid displaced? The person who found that is Archimedes. You might remember his story. The king gave him a crown, and it was a beautiful crown, gold on the outside. But the king wasn't convinced that the jeweler who made it out of complete solid gold. And he was worried that the jeweler had taken part of the gold and filled the inside of the crown with lead. Archimedes' task was to figure out whether or not the crown was solid gold all the way through without cutting into it because he didn't want to destroy the crown. Archimedes said, oh, well, if I could just figure out the density, I could figure out whether it's the density of gold or the density of lead or somewhere in between it. But how do you measure the volume of a very elaborately designed crown? The story goes that Archimedes was thinking about one day, had filled his bathtub completely filled with water, and when he got into the bathtub, he noticed that water, of course, went over the edge. And at that point, he realized, wait a second, the volume of the water displaced by my body is equal to the volume of water that went over the edge. And he realized if he could collect the water that went over the edge of his bathtub, he could measure that volume, and he'd know the volume of his body. At that point, the story goes, he ran through the streets of Syracuse, a city-state in Greece, yelling Eureka, which means I found it in Greek. And he may be the first recorded instance of a streaker running through the streets of Syracuse. So using this idea, you can either measure it this way. In this case, if we drop this rock into a full beaker of water and measure the water that came out, the volume of the water here would equal the volume of the rock. Likewise, you could just drop the rock into a partially filled beaker, and this volume right up here, where the water moves up, would be equal to the volume of the water displaced, or the volume of the rock. Interestingly enough, Archimedes' principle states that not only is the volume equal, but he stated this: an immersed body is buoyed up by a force equal to the weight of the fluid it displaces. So take a quick look at this one. So this mass weighs 3 kilograms. And notice that right now we got an empty container over here. It's tared to zero. When I submerge it, this mass is going to displace liquid. Notice now that while this mass is submerged, it seems to weigh less. Why? Because there is a buoyant force acting up on it. And notice that the liquid that it was displaced was 2 kilograms worth of liquid. Sure enough, this is a kilogram mass. I guess it could be a Newton mass as well, or a Newton measuring device. Let's make it newtons. In this case, the mass weighed 3 newtons before you put it in. What happened in this case? It now weighs 1 newton. Why? There must be 2 newtons of force acting upward on it. And Archimedes, said that's equal to the weight of the water displaced. There must be 2 newtons of water displaced. That's the force of gravity on it, or about 2 kilograms of water displaced. 0.2 kilograms of water displaced. You can use Archimedes' principle to actually describe how things float. Why do steel boats float? You're like, wait, steel should sink in water. It's more dense than water. Yeah, it's true. But what's happening here is as long as you have air inside that's displacing water, you get a net upward force on the boat. So take a look at this short video, which I hope plays. Maybe not. There we go. This steel boat here travels through water. Why does it float, even though the steel is more dense? The answer is below deck we have a large amount of empty space. What's happening here? We're displacing this much water. And Archimedes' principle states the weight of the water displaced. In other words, the force of gravity on this water that is being pushed aside by the boat is equal to the net upward force on the ship, the buoyant force. And as long as this buoyant force is equal to the force of gravity, this ship will float. And that is basically the key. We need the weight or the mass of the water here to equal the weight of the boat. I'll call this F sub B for buoyant force. You might say, wait, could the buoyant force be larger than the force of gravity? It could be, but what case would that happen? The ship would accelerate upward. What would happen if force of gravity is greater than buoyant force? Then the ship would accelerate downward. Hopefully at that point it would displace more water and it would stop accelerating downward, but if it is overweighted, it will continue to sink and go below the water. The ship will sink. So ships float by just displacing a water equal to its own weight. In this case, this water, or the volume of water displaced right here, the weight of this water must be exactly equal to the weight of the ship. And as long as it does, it'll float. So couple of quick check questions. Does Archimedes' principle tell us that an immersed object displaces liquid weighing 10 newtons? The buoyant force in the object is 10 newtons? Take a second, think about it. Answer on this one is yeah. Literally, that's exactly what Archimedes' principle states. The buoyant force is equal to the weight of the water displaced by the object. Here's a little trickier one, a mathematical one. A 1 liter container is completely filled with lead, has a mass of that, and is submerged in water. What's the buoyant force acting on it? Well, to answer that question, we've got to figure out, all right, how much water does a 1 liter container displace? Well, a 1 liter container, you might remember, is 1,000 milliliters. 1,000 milliliters, when we're dealing with fresh water, would be exactly 1,000 grams. 1,000 grams, or of course, 1 kilogram. So 1 liter is displacing 1 kilogram of water. Well, what's the weight of 1 kilogram of water? I'm going to go a little more precise in this than I sometimes do in physics. I'm going to say that gravity is equal to 9.81. And this becomes important later when you're doing your ship calculations, 1 meter per second squared. And so what is the force of gravity on the water, or what's the weight of the water displaced? The answer would be 9.81 newtons, just to figure out the force of gravity on it. And so what's the buoyant force on this water, or on this thing that's displaced? The answer is it should be the force buoyant, F sub B, should be 9.8 newtons. And again, we're assuming that this thing is completely submerged. Whoops, ignore that little line there. I should have been a little slower. This is all underwater. Will this object sink or not? The answer is yeah, it'll definitely sink, even though there's a buoyant force acting on it. Because it has 11.3 kilograms, we've got over 100 newtons is the force of gravity. Yeah, this thing is going to accelerate downward. Force of gravity in this case is much, much larger than that. It's about 110 newtons to 3 sig figs. It's going to fall. Yeah, this thing's going to accelerate downward. Yep. You can calculate the buoyant force on an object with the following formula. Buoyant force equal to the weight of the water displaced. Well, the weight of the water displaced is just equal to the mass of the water times gravity. Mass of the water is equal to volume times density. Remember, density is defined as mass per volume. And so if you rearrange that, you can calculate, oh yeah, mass is equal to density times volume. Now, I'm not going to use D for density, even though I did it here just for a moment. In physics and in engineering, rho, the Greek letter rho, which sort of looks like this, is the character we're going to use for density. Volume is V, density is rho, gravity is G. However, you'll usually see this formula written with rho in front, so rho GV. So buoyant force, density of water times gravity times volume. Now you might say, oh, I know density of water, it's 1. Well, in chemistry, it's 1 gram per cubic centimeter. In physics, we always use kilograms and cubic meters, so density of water is going to be 1,000 kilograms per cubic meter. Quick reminder about sinking and floating. Typically, if an object's denser than the fluid in which it's submerged, it will sink. So if you put a paperclip on water, it'll sink. If the object's less dense than the fluid in which it's immersed, it'll float. So styrofoam on water floats. If it's equal, it's neither sinks nor floats. So most fish have the same density as the water around them. You might say, wait a second, Mr. Kalmer, you just said steel will sink. Yeah, unless you shape it into the right shape. And again, ship hulls are designed to displace a weight of water greater than their own weight so that they can actually float. So We already talked about this. How do boats work? Well, they're designed to displace enough liquid so that it can hold up the weight of the thing inside of it. This hippo sitting in the canoe displaces enough water, or the weight of the water equal to the weight of the hippo in the boat. And the same thing's going to apply here. And we're going to talk a little bit more about this in a second. I would do the mathematics. Quick question, is it easier to float in salt water or fresh water? Yeah, most of you can figure out this one already. The answer is salt water because it's more dense. You don't have to displace as large of a volume as you would in that. You'd see most of your body is about the density of fresh water, give or take how much air you're breathing or holding in your lungs. If you were immersed in pure alcohol, ethyl alcohol, you would sink because its density is much less than your own. Most of you have heard the story before. The tip of an iceberg, only about 10% of an iceberg is actually above the ocean surface. Why? Because ice is 0.9 times the density of water. So to hold itself up, 90% of it is going to be submerged and only 10% above the water itself. Floating icebergs, you can actually take them. They're actually kind of fun. You can tow them around. Recently they towed an iceberg from Newfoundland down to an area that needed fresh water, let it melt in a lagoon, and you can get some amazing ones. All right, how does this apply to your boat? Here's the part I need to get to today. Let's say in your group you decide who's going to be your pilot in your boat, and you measure their mass and decide they're 75 kilograms. The boat itself, you calculate, is going to be about 2.1 kilograms. This is the shark boat that's actually up on the side here in the room, or it might be up front. My question is, how deep was this boat going to sink, given the measurements that you see? And these are its actual measurements. To do the calculation, we know the buoyant force is going to be equal to rho times g times v. In this case, we know the buoyant force has to equal the force of gravity once it reaches equilibrium. The buoyant force in this case has to equal the force of gravity on the boat and its rider, these two numbers, times gravity. The density of water is 1,000. Gravity, I'm going to use the more precise measurement of 9.8, and I'm going to calculate the volume of water that we need to displace. If you solve this one, you'll discover, okay, it's got to displace 0.0771 cubic meters worth of water. So now, how deep is that going to sink? Well, to solve that one, we first of all need to figure out the areas of these two sections. The area of this rectangular portion is 0.442 square meters. The area of this triangular part, just 1/2 base times height, is that. And so now we can actually think about it. I'm going to just draw it as a rectangle here to make things simple. My question is how deep is it going to sink? I'll call that delta x. Now here it might require a little bit of logic, and I might have to do a little bit of drawing here. The volume of the water displaced is going to be equal to the depth that this boat sinks, delta x, times the area of the bottom of the boat. If you think about that as being like a rectangular solid, it should actually kind of make sense. So we're going to assume the boat sinks that, and my apologies, I'm not drawing this very well. But we can now use this. The volume of water displaced is equal to the area of the bottom of the boat times delta x. For those of you who have curved bottom boats, I should actually mention this. This gets a little bit more exciting, and partly why the Noah's Ark one didn't work very well. To find the volume of water displaced, you're going to have to actually integrate this area. That requires some calculus. I will help you with that if you need it. But in this case, the area is just the sum of the rectangular portion and triangular portion of my boat in square meters. The volume we have to displace is this volume from up above. And so if you solve this, you'll discover that the shark boat, with a 75 kilogram person sitting inside of it, would sink 0.117 meters, or 11.7 meters deep. Hopefully that makes sense. All right, good luck everybody. Hopefully you can start designing on your boats. And we'll talk to you soon.